Good afternoon. We're going to go over 16.2 notes, part 1. For an endothermic reaction, we have the reaction progress on the x-axis and energy increasing on the y-axis. So for endothermic, the energy is going to go up. So we start at a lower energy, we end at a higher energy. These are our reactants down here, and these are our products up at the top. For an exothermic reaction, we have the opposite process. Energy increasing and reaction progress. The energy will start higher and end lower. So our reactants are down there, up there, and the products are down here. Okay, doing one just to give you guys an idea with some numbers and labels. If we start at 0 with our reactants and end up here at our products, let's say each line is 100, so we are ending at the 200. We have technically put in 300 kilojoules, but we've gotten back 100 at the end. So the total right here, from here to here, change in energy or enthalpy of the reaction is going to be the difference between the two. The ending 200 minus the initial 0 would be 200 kilojoules in this example. So it's positive because we are going up. If we had another reaction where we started up high and ended down low, and we always start at 0 because we're actually looking at the difference between the two. And we would be ending here at negative 200. Okay, so the total change, delta H right here, negative 200 minus 0 would give us an enthalpy change of negative 200 kilojoules for this reaction. So exothermic, it's negative, heat is coming out. Endothermic, it's positive because heat is going in. Okay, so that's what this is saying right here. The enthalpy of the reactions. It's the final minus the initial, and you will get positive for endo and negative for exo. Stability and enthalpy of formation. So if the delta H of formation is negative, that means the compound is stable. It's like rolling a boulder up a hill. Okay, so if we were talking about an endothermic reaction here, and we have a boulder at the bottom, we are pushing it up to the top of the hill, we are forcing this process. Okay, we're going to have to add energy to get the boulder up to the other side. So that's endothermic. So if we're talking about the formation of some kind of compound, we're actually like forcing this process to happen. Whereas if I have an exothermic reaction, so let's say we're forming water. Water is down here, and its individual elements that it's made of, H2 and O2, have a higher energy up here. So once I get that boulder to the top of the hill, it is going to roll down here all on its own and give off. It's going to release. In this example, with the boulder, it'd be turning it into kinetic energy, and that boulder would roll on its own. In this example, we're talking about enthalpy. It's going to be given off as heat coming out of this reaction. So which is more stable? This one, let's call this A, product A or product B. Well, product A is a lot more likely to have the reverse reaction happen and break down into its parts. So the stability of A is low. Low stability up here. That is messy writing. So this is low stability. Low stability up here. Right here, water is very stable. That's why it's present everywhere on the earth. So Water is low energy. Hydrogen and oxygen are higher energy. When you have a balloon full of hydrogen and you add a tiny bit of energy to it, you get a huge amount of energy given off. And so the product, the water that's formed, is very, very stable. So this is high stability. Okay, stability. All right. Thank you guys. Have a great day.